invite Tejendra Thakur. He is going to talk to us on hydrogen bonds between same charge species, insights from computational studies.
Good afternoon, everybody. First, I would like to thank Professor Arunan for inviting me to this very special meeting for on hydrogen bonding, because hydrogen bonding is so ubiquitous, so common, and finding a conference very specifically on hydrogen bonding is nowadays very rare. I am very thankful to him also for the inviting all these experts who are looking at that elephant and the different perspectives into this conference, and we have all variety of crystallographers, spectroscopists and biologists and theoretical chemists also in this conference. So, hydrogen bonding phenomena is so common, but we come across this hydrogen bond very frequently, but we do not have worked much on the fundamental understanding of this type of hydrogen bond much. But recently 6 months back we published a study on same charge species, hydrogen bond in the same charge species, which I like to present today. I will start with the definitions which was proposed few years back, which describes the hydrogen bonding in the current context. Over the year of 100 years, our understanding to hydrogen bonding have improved a lot, and we have moved from a very rigid conventional hydrogen bond definitions Pauling type, where we have moved from highly electromagnetic atoms to very weak donors like CH also. But the definition suggests there are few important points which are now includes all type of interaction, whether we are strong and weak. First important part is the interaction has to be very interactive in the nature. Second, it is a local interaction between the two fragments. One is hydrogen bond donor, which is XH, and hydrogen bond acceptor, which would be YZ also in the case, and it has to be supported by the evidences which confirm that there is a bond formation, and these evidences and also were discussed in the definition that can come from anywhere from experimental studies or theoretical studies, experimental from spectroscopy, NMR, also from calorimetric measurements where we can estimate the strength of these hydro bonds. So, basically all these definitions try to present hydrogen bond as energy continuum, a borderless definition where all strong and weak type of hydrogen bonds are included into one page. We have very strong hydrogen bonds which have quasi-covalent character, and the very weak type hydrogen bond where the correlation component becomes quite significant. Similar definition are being observed when we study the experimental and theoretical charge density approaches, and we see a clear cut increase in the accumulation of charge density at the bond critical point between the interacting hydrogen bonding atoms. The most important among these is that the shortest one and most strongest one, which are the charge assisted type of hydrogen bond. They are very special, where we see hydrogen bond stabilization is accentuated by the presence of electrostatic interaction. Namely, we have a charge donor which have a neutral acceptor with having a ion dipole type of electrostatic interaction which is enforcing that hydrogen bonds. We can also have a doubly charged system where we have a positive on the donor and negative on the acceptor, and we have a highly strengthened hydrogen bond in the cases, and we have seen this kind of hydrogen very are in the very high energy range and have a very particular quasi-covalent characters. Another situation can also be thought of where these electrostatic forces are not favoring these hydrogen bond formations. The hydrogen bond stabilization in the case has to face the repulsions and destabilizations causing from the same charge species. These can be categorized at same charge hydrogen bonds, either of cationic type and anionic type. Although these kind of interactions were quite common, but not to totally remain ignored for quite long time. However, there were few cases where people have found some peculiarity or deviation from the standard existing models, like the discussion on this colloidal particles arranged in a liquid crystalline type of arrangement, where we see a strong interaction between the cationic charge particles. Here in the words, the charge particle distances were quite short, which was not predicted by the standard models. So, which says that there is some kind of interactions which is happening between the same charge species. A more detailed discussion was cropped up when Braga et al. Reported a crystallographic study of a anion type of hydrogen bond and said that these hydrogen bonds are not the real hydrogen bonds, where the standard strength and length analogy, which is the core of all hydrogen bonding concept, is not followed, and this was followed by several discussions. The main point of the study was they studies the oxalate salts, potassium hydrogen oxalate salts crystal structures, and found out that these cations and anions are arranged in the separate layers, and the anions are hydrogenally bonded to each others, because the hydrogen bond distance OO distance were quite short, which are not even shorter than the regular neutral hydrogen bonded OHO systems. So, they found that these interactions are very different from the normal hydrogen bond, and they are very short. And when they computed the interaction energy or the binding energies for this anion-anion pair, they find they are highly destabilizing in nature. So, they came up with the conclusions that the strength versus distance analogy, which was a hallmark of all hydrogen bonding type of interactions, is not followed in these same charge species type of interactions. And they said that these are not the real hydrogen bond, that may be called as a pseudo hydrogen bond. The reason they are being observed in crystals is because of the counter ion interaction between the potassium ion and the oxalate anions, which is bringing a push pull effect, which is simply like a Tarbert effect, which holds these two anions to very short distances. But this was contested by another famous researcher, Steiner, and they said if you look at not only look at the distances what we observed in crystal structure, we have to look at those evidences which come from spectroscopy, which shows clear signature of this OHO type of interaction in solutions. So, based on that, they said that it is not correct to compare these distances, short distances, which we say in the observed in the case of anion-anion, to neutral hydrogen bonds. You should compare with other charge assisted hydrogen bonds, whereas these distances were quite common, and this pattern where that distance between the hydrogen bond distances between the hydrogen and oxygen and hydrogens follow this kind of curve. Further evidences start cropping up on the same systems, where Maskell et al. Studied and confirmed the presence of these OHO interaction between the two anions from the NMR, and they have observed a standard hydrogen bonding isotherms for these kind of interactions. Moreover, they also calculated the association constant in these cases and found out that these are comparable to very strong hydrogen bonds. But of course, the stabilization energy when we compute for these anion-anion pairs remains highly positive. Further, in the same system, evidences from the charge density analysis were also brought in by Maki et al., and they found that there is a local attraction which is happening between the hydrogen of one carboxylic anion and the oxygen atom of other oxygen. So, all these evidences shows are very peculiar of a true hydrogen bond type of interactions. Also, these Laplacian maps show that there is a local concentration of charge which is quite high in the case of these anion-anion interactions, which show there is some incipient covalent character which is being cropped up in these kind of interactions. Although again in the cases of if you compute the interaction energy in these cases, these were still positive in these cases. Espinosa also tried to understand this anion-anion type of interaction with a similar type observation, and they said that this local interaction is always attractive because you find encroachment of this electron density from the oxygen atom in the this influence zones of hydrogen incipient hydrogen bonds hydrogen atoms, which is coming from the donor side. So, both of these says that there is some kind of local attractive interaction in the case, but what people earlier were proposing, because since these dimers are destabilizing, they could not be called hydrogen bonds. But similar, but there were not much cases where the cation-cation interactions were observed, but recently we saw some increase in the report on the cation-cation type of attractions or type of hydrogen bond being observed in the cases where we have similar short hydrogen bond characters. Recently, this discussion on short repulsive type of contacts were again cropped up when Winhold again tried to explain these hydrogen bonds as very different hydrogen bond than the normal hydrogen bond, and they termed it as anti-electrostatic hydrogen bond. Although they tried to stress more upon the covalency factor, which is obvious in the case of very short hydrogen bonds, as the important factors which is responsible for their stability in these cases. So, we also thought that we will try to look this kind of system, and we had few questions in mind. The first one, whether these interactions were really different from hydrogen bond or they are same as hydrogen bonds. If they are same, what is whether they are stabilizing in nature or not. And one other important which was there, that what we see in the solids is the effect of counter ion, which is bringing those molecules or anions to close enough to form a hydrogen bond, is a result of Coulombic compressions, which is coming from the attraction between the two counter ions. If this is two hydrogen bonds, and we already know that there are Coulombic interaction between two anions or two cations are dominant, and trying to destabilize this interaction can somehow we can overcome these interactions. This was also a question in our mind. Considering this, we tried to find out some suitable system, and we came across a very a system where we found that different salt of this natural product sulfurenes show a lot of these cation-cation type of interactions in their crystal structures. And we found that there are several associated cation-cation species which are hydrogen bonded by very strong OH type of interaction, and having multiple, ones strong and one weak and totally weak, and sometimes water mediated interaction in this crystal structure. Also, along with that, we also find rather than cyclic dimers, long chain dimers, which is also present in these systems. So, we try to understand these interactions from computational studies. So, first what we studied, we tried to see that whether these cation-cation interactions are really different from various aspects compared to the normal bonds. What we did, we take that cationic-cationic OH dimer and compare it with the same similar neutral dimers. When we see the geometrically, we found that these dimers are short in the case of short and more linear in the case of cation-cation bond, but the stabilization of binding energy in this case remain positive, whereas neutral show typical binding energies for a strong hydrogen bonds. Electron density features also were very different in the cases. The neutral bond here in this case, which show the two hydrogen bond character are having high electron density at bond critical points, but the hydrogen bond which are supposed to be not there if there is no interaction show equally strong hydrogen bonding characters with high electron densities at the bond critical points. The local covalency character also was computed from various NBO analysis. This also supported that when we have cation-cation OH hydrogen bonds, we had a strong delocalization happening because of the short nature of these kind of interactions. Then we try to see that whether there is a real hydrogen bond character in these type of interaction, and we compare the potential energy surfaces for these cation-cation hydrogen bonded species and compared with the neutral species in these cases. What we found that these potential energy surface were not very same. They show very peculiar feature, especially in the case of cation-cation hydrogen bond with a observation of a energy barrier which is not there in the cases of normal hydrogen bonds. So, what this suggests that there is some during this range that repulsive energy component is dominant and controlling the total energy of the system, whereas as we go down we start seeing this minima which is typical of a hydrogen bond coming from the attractive energy component of the hydrogen bond possible in the case of cation-cation interaction. The overall energy profiles remain in the positive side in the case of these cation-cation interactions. We looked when we compared it for the weaker type, that this minima become even shallower, which is also very quite similar for the neutral cases, because these hydrogen bonds are very short, very weak in nature. So, from these comparison we came to know only that the signatures which the evidences from the theoretical studies were quite similar for the hydrogen bond, whether it coming from the cation-cation species or anion species. But when we see the R dependencies in the potential energy surfaces, they have a distinct behavior. We saw a emergence of dissociation barrier in the cases. So, especially in the case of weak hydrogen bond, this dissociation barrier was also low, and that minimization, the well depth was also very small, which shows which in some cases were unbound, especially when we do not have the cyclic dimer cases. So, then we thought that let us compare what the stabilization nature of these interactions in somehow from the computational studies using this simple supramolecular method, and we found on all the cases we have positive binding energies. Even for the stronger case we have less positive, and when we have one strong and one weak, the range was still in positive range. When we have weaker, we have even large destabilizations for this binding binding energies which is in the positive range. But some peculiar cases were also observed where we have very short cations are coming very short distances, and the stabilization energies were very low in these cases. Singly hydrogen bonded cation-cation species remain highly destabilizing in nature. So, when you look at the geometry, what we observed in the crystal structures, we find very short and very linear even for the weaker cases in this all these structures. So, we thought of just to estimate the strength what we can get from this hydrogen bond formation. Let us compare the say two geometries when we have a cation-cation interaction in the crystal with a neutral case when the coordinates remains totally unaltered in the two cases. When they compare that the same trend what we see in the OHO case, stronger case we have stronger binding energies for the neutral case, and weaker case shows the weaker interaction energy. That says that that gives us a hint that the both, whether the hydrogen bond in the cation case or the neutral case, they are giving the similar trends in terms of binding energy, whether they are in positive side or negative side. We also looked at the topological features which are obtained from the reduced density gradient surfaces, and try to understand this local interaction and contribution for other interaction in these cases. We took these two specific cases of very strong and very weak hydrogen bonding pairs, and we found these hydrogen bonds show typical features of strong interactions in these cases. Even the weak hydrogen bonds also show pronounced local attractive interactions between these hydrogen bonds. And the charge density, when we compared for these crystals, these molecular pairs in the crystals, we found that even for these weak CHO interaction, this charge density was quite as comparable to the strong and quasi-covalent type of hydrogen bonds. So, we thought that this is not the correct way to look at what could be the possible reason that these interactions are very different, and why this is there any really contribution from this hydrogen bonds, so which in this cation species. Then we thought of comparing the potential energy surfaces for the same cationic hydrogen bonded species with a non-hydrogen species. In this non-hydrogen species, what we did, we just changed the orientation of these OH groups to get a geometry very similar to same geometry, except the hydrogen atoms were changed to dihedral for this OH groups has changed from the hydrogen bonding to a 90 position, which gives a geometry which is totally non-hydrogen bonded in this case. And we compared the profiles of these two cases. When we see these cases, we clearly see in the case of non-hydrogen geometry there was no more stabilization, and we see clear cut stabilization coming from the hydrogen bond in this cation species. And these were very similar when we compared it to the neutral case. The non-hydrogen geometry do not show much stabilization compared to a non-hydrogen compared to a hydrogen bond geometry. And few other peculiar feature which are observed in these cases. In the case of cation species, we see this attractive interactions coming to dominance at very short distances compared to the neutral cases. And also the minima depth, which in case of cation species was much higher compared to the neutral cases. We say, which gives an indication that this hydrogen bonds in this cation species are real hydrogen bond. They are giving even larger stabilization compared to the normal cases. So we thought of, let's look at this energy contribution from various these cation species in these hydrogen bonds in this cation species, and compare it with the hydrogen bonded and non-hydrogen bonded to get a clear idea which are the contributing factors which are working in this case. When we compared the hydrogen bond geometries and non-hydrogen bond geometry of cation and neutral species, we found that electrostatic energy which is contributing to these hydrogen bonds were very similar in the neutral and cation species. However, the large differences were observed in the cases from the polarization effect. The polarization was more dominant in the case of cation, which is contributing more to the stability of these cation species. So what we saw is the dominance of these short attractive forces, which were quite obvious from the potential energy surface profiles for this cation species, which say that there is a definitive local interaction between this, although having a counteracting electrostatic interactions have a attractive feature. Though the overall binding energy shows clearly that they are not able to overcome the electrostatic destabilizations coming from these same charge interactions, and that lead to a shifting of the equilibrium between the attractive energy component and the repulsive energy component to a shorter distance range compared to the neutral cases. The polarization factors becomes a prominent factor which is very distinct from these routine normal hydrogen bonds in the case of cation species. So then we thought that let's try to understand better that whether what we are distances and linearity observing in the crystals is a result of packing and or Coulombing compression which is present in the case of solids. To study that, we just compare the gas phase topology of electronic distribution in the crystal environment and the gas phase. So topology also show very similar properties in the case of gas phase and the cationic phase. However, the distances between the hydrogen bonds were much shorter compared to the crystal, which shows that definitely the packing and other crystal fields effects are forcing them to come to much shorter distances compared to the cationic gas phase calculus. We also looked at the change in the electrostatic potentials, and we saw clear distinction. The charge is more concentrated on the cationic fragment, which is ammonium fragment here in the case of crystals. However, but the complementarity between the hydrogen bond groups, where hydrogen bond donor hydrogen is showing high electrostatic potential, positive potential, whereas the acceptor is showing the negative electrostatic potential. Similar features were observed in the gas phase monomer, but in the cases this charge distribution is much more anisotropic compared in the ammonium fragment. However, when we try to make a dimer in the gas phase, the same features start appearing up, and we see clear polarization happening from monomer to dimer in these cases. But still in the crystal case, that this amount of increase in electrostatic potential was much higher in the case of crystals, which clearly shows that there are some crystal field effect, but definitely it is not because of the counter ion which is giving rise to this polarization effect coming in the hydrogen bonding stabilization. So what we saw that the hydrogen bond adopts a very short and linear geometries in the crystal dimer than the gas phase dimer. We say there are some effect, but that quasi-covalent factor was still seen in the gas phase dimers, but the shortening was much more in the case of crystals. MSPL values also show there is an increased polarization which is seen from going from the gas phase monomer to dimer and then to crystal structure. However, the electrostatic terms again remains quite large and significant and larger distances, which also lead to enhanced polarization in the crystal environment due to the presence of other counter ion in the cases. We also see that the hydrogen bond cationic systems were quite stable, because all these minima in the gas phase were corresponding to a stationary point in the gas phase. However, their binding energy will remain the positive in the cases. So we thought that if the binding energies are still positive, how we can overcome this destabilization which is coming from the hydrogen bond from the same charge electrostatic repulsions. So we could go back and then looked at these hydrogen bonding species and their distribution from the charge center, which we found in all the cases of salt crystals, that positive charge is localized around the ammonium fragments. So in all these hydrogen bonding species, what is the distance distribution between these N positive charge species, and what is the total contribution from the destabilization energy in this case? We found a linear relationship. A shorter the distance have very high destabilization, which is particularly obvious coming from the electrostatic repulsion between the same charge species. However, in one particular case, when we have hydrogen bond dimer, the binding energy was, although very positive, it was very totally different from the trends from other molecules, other cationic species. This says that this hydrogen bond may be playing some roles in improving the stabilization from hydrogen bond, reducing this destabilization caused by the same charge species. So when we computed, we saw that with this hydrogen bond, specifically that waters are providing more stabilizations to this cation species, which allowing them these charge species to come at very short distances. That is why this electrostatic repulsion basically get weakened by the dielectric shielding of the solvent medium. If you compute the same interaction energy in the solvent medium, we further reduction in the destabilization caused by this cation repulsions. We thought that if this is possible, then we can further go from this negative positive binding energy to negative binding energy, which is typically seen in mostly all kind of hydrogen bonding systems through hydrogen bonding. We screen many systems and come across a multiply hydrogen bonding system where we clearly shifted the stabilization to a negative side, where we can see this kind of effect can be totally nullified. We can clearly overcome this electrostatic repulsion caused by cation and reach the stability from the hydrogen bondings. So basically we are trying to counteract this repulsive component, energy component through attractive hydrogen bonding component, which is positive side on the, in the case of cation-cation hydrogen bond, and increasing the multiple hydrogen bonded, we can further reduce it to the negative side. So, we also studied some doubly hydrogen bonded studies. This was the same effect where we can increase the hydrogen bonding to increase the stability component from the attractive side. We can also increase the destabilization by increasing the charge. In these cases, we again saw similar hydrogen bonded, very short and linear hydrogen bonding, even in the case of weak hydrogen cases. But when we compute the energies, we saw clearly there is destabilization coming from that the CHOs were not able to overcome the destabilization from the coming from these charge-charge interactions. So, basically what we observed that when we have multiple hydrogen bonded systems, we can reduce this at a same charge species interaction, and we can do it either through solvent incorporation or through increasing the number of hydrogen bond between the two cations. So, we can shift this hydrogen bond minima from unbound down to bounded side in the case of multiple hydrogen bond species. So, in the summary, what we although we do not claim that we try to understand it very well, but try to answer to some of these questions where we find these interactions are not very different. They are of charge type of hydrogen bonding type of interactions, and they are definitely stabilizing, but they are largely not able to overcome the Coulombic repulsion in the journal. But you can do that when we increase the number of hydrogen bond or include solvent type of interaction between the two cations. That is all, and thank you for your attention. This work is done mainly by my student Shivanand Das, and the later part where we shown some dicatonic species, this is done by Dharmendra. Thank you very much for your attention.
Thank you, Thakur. Time for a couple of questions. People are hungry, I know.
Maybe I missed your, most of the quote unquote binding energy you showed was positive.
Yes.
But when you showed the potential energy curve, I saw for cation there was a small barrier and then it was going below the product limits.
Yes.
That must have been negative, isn't it? But I don't remember seeing anything in your.
You means that
when you showed the potential curve for neutral and cation.
Yeah, this one.
I thought it was bound.
Yeah, this one.
Yeah, isn't it below the product limit?
No, it is still above 0, but definitely what you see, the unbound and bound hydrogen bonding so much.
We had one more, but I thought it was bound. Another thing, you did the BSSC correction at the minima.
Yeah.
Did you do the BSSC correction all the way?
All are with BSSC correction.
No, but did you do the BSC correction along the whole
PS also?
Along the coordinate?
Along the lines. This is with BSC corrections.
Yeah, it's almost a follow-up question actually. If you really were to include solvent fully in the computations, would you have a decrease in this repulsion part?
Yes, we have seen the decrease in the repulsion.
How low can you make the repulsion?
Not very low, like directly if I weaken the electrostatic attraction also, repulsion also, it weakens little bit, but not very much.
Computationally, if you use a very high,
but in some cases it may go to the negative side of the binding energy, but not that much high, which you can guess. But the hydrogen bonding create lot of differences. If you increase the number of hydrogen bond between the cation species, so then it goes drastically, especially in the cases where we have quadruply hydrogen bonded, so it becomes totally negative from the positive side.
Okay, are there definite examples from the X-ray structure which correlates with this?
So starting all was
in terms of frequency of the
stretching frequencies, we have not studied in our cases, because the recent part we want to study where we have really got the negative binding energy in the gas phase also, and we have synthesized those compounds also, and we are trying to see the spectroscopy and even crystallography of that one. So maybe I have not, but in earlier cases which has been reported for anion species, definitely they have seen the shifts similar to hydrogen bonds, red shifts.
Okay, thank you.
So where are your anions? I mean, there should be anions also, counter anions.
This is we have studied the whether these cation species in the isolated case they are stable or not, and in the case presence of anions also they are obviously they will be stable because these attractive interaction
somewhere
also
around it may be hanging around somewhere. No? So
Is it
that will
in the
also have some influence stabilizing it.
Yeah, definitely that influence is there. That's what I said. The crystal field effect and Coulombic pressure are playing some effect, but not that much that these will not be observed in the gas phases.
Okay.
Okay, if there are no questions, let me wind up the session with a question from me.
Yes, sir.
In the crystal calculations, did you include the periodicity
Yes,
component?
yes.
You have. So you use the
No,
crystal.
no. For
Okay.
which calculations? Sir?
For the comparison of the dimers in crystal as well as in the gas phase.
No, no. On that cases, I have taken the crystal geometries and then compare it with the. But all the
So
cases.
effectively, you have introduced the symmetry.
Yes.
Okay. So if no more, we will end the session, and I thank every one of you, every speaker for keeping the time.